Hi, welcome back. I'm Professor Ronald Vincent M. Santiago, and today we'll be discussing Module 16, Problems on Case 1, Unloaded Generators, Double Line to Ground Fault. Let us consider now a power system as shown in the diagram. A double line to ground fault occurs at bus 4. Assuming zero fault impedance and neglecting the loads, find the phase currents in transmission lines L2 and L3. So we are given here the different parameters of the different components. Transformer T1 or T is equal to X equal to 0.08, G1, generator 1, the reactances are X1 for positive sequence 0.4, X2 negative sequence 0.4, and X0 zero sequence reactance 0.15. For generator G2, the positive, negative, and zero sequence reactances are given 0.5, 0.5, and 0.25 respectively. L1 for transmission line L1, the reactances are given X1 and X2 are equal, X0 equal to 0.80. L3, transmission line L2 rather, X1 and X2 are equal, X0 is equal to 0.6. Transmission line L3, X1 and X2 are equal, X0 is equal to 0.4. Now, drawing the positive sequence network as shown in the diagram, based on how the given circuit is connected, the network cannot be simplified as shown using series parallel combination. We have to use a delta Y transformation. So thus, converting now the delta connected configuration of the impedances or the reactances 0.2, 0.4, and 0.3 into a Y connected configuration, XA, XB, and XC, XA is now equal to 0.067, XB equal to 0.133, and XC 0.88. All are in per unit values. Thus, we now have the equivalent circuit of the given system. Solving now for the left-hand side of the system, the reactance at the left-hand side, XL is equal to 0.4 plus 0.08 plus XB equal to 0.6133. Whereas for the reactance at the right-hand side is equal to 0.5 plus the reactance XC 0.5888. Now, solving for X1, the positive sequence reactance measured at the voltage point F1 and the neutral point N1, that is equal to XA plus the parallel combination of the left-hand reactance and the right-hand reactance. So that gives us 0.3671. So thus, we now have a Thevenin equivalent network of that given system. We have X1 already given. Note that X1 is not equal to X2. For the zero sequence network, we now have this interconnection. So we have a system here, how it is connected, considering now the transformer, how it is connected. Is it Y grounded, or delta delta? In our system, it is delta Y grounded. So now, again, we need to transform the delta connected reactances into Y connection. So thus, we now have XA to be equal to 0.133, XB to be equal to 0.267, and XC equal to 0.178. After converting the reactances from the delta connection to Y connection, we can now compute for the left-hand reactances to be equal to 0.08 plus XB to be equal to 0.3467. For the right-hand side reactances, that will be equal to 0.25 plus XC equal to 0.4278. So thus, x0 is equal to xa plus xl in parallel with xr. So that gives us the zero sequence reactance to be equal to 0.3248. So connecting all these zero sequence, networks, sequence networks, positive, negative, and zero sequence networks in parallel, we can now compute for the current IA1. We let our Thevenin voltage to be equal to 1.0 angle 0 degree per unit. So thus, based on that figure, that interconnection of the three sequence networks, IA1 is equal to 1.0 angle 0 degree divided by J 0.3671 plus the parallel combination of the reactances of the negative sequence and the zero sequence network. So thus, it gives us IA1 to be equal to negative J 1.8538 per unit. By current divider, we can solve for IA2 to be equal to the negative of IA1 multiplied by 0.3248 divided by 0.3248 plus 0.3671. And that gives us J 0.8703 per unit. And by Kirchhoff's current law, we can solve for IA0. And that gives us negative IA1 minus IA2 to be equal to J 0.9835 per unit. Thus, for the phase currents, we can now solve for IA during the fault. IAF equal to 0, IBF equal to IA0 plus A square, IA1 plus A, IA2 to be equal to negative 2.3591 plus J 1.4753 per unit. ICF is equal to IA0 plus IA1 plus A square IA2 to be equal to 2.3591 plus J 1.4753 per unit. Now, solving for the sequence voltages at the fault, that is at bus 4, BA0 at bus 4 is equal to BA1 at bus 4 equal to BA2 at bus 4 equal to negative IA0 J0. And that gives us negative J 0.9835 multiplied by J 0.3248 to be equal to 0.3195 per unit. The positive sequence voltages at buses 2 and 3, Ix is equal to negative IA1 multiplied by 0.5889 divided by 0.5889 plus 0.6133 to be equal to negative J 0.9081 per unit. BA1 equal to 1.0, that is at bus 2, plus J 0.9081 multiplied by J 0.48 equal to 0.5641 per unit. IY is equal to negative J 1.8538 plus J 0.9081 to be equal to negative J 0.9457 per unit. So thus, for the positive sequence voltage at bus 3 to be equal to 1.0 plus J 0.9457 multiplied by J 0.50. And that gives us 0.5271 per unit. For negative sequence voltages at buses 2 and 3, we solve for Ix to be equal to negative IA2 multiplied by 0.5889 divided by 0.5889 plus 0.6133 to be equal to J 0.4263 per unit. At bus 2, BA2 is equal to negative J 0.4263 multiplied by J 0.48 equal to 0.2046 per unit. And solving for IY, that is equal to J 0.8703 minus J 0.4263 equal to J 0.4440 per unit. Thus, for BA2 at bus 3 is now equal to negative J 0.4440 multiplied by J 0.50 equal to 0.2220 per unit. Zero sequence voltages at buses 2 and 3 can now be shown as BA0 at bus 2 equal to 0.435 per unit and BA0 at bus 3 0.1101 per unit. Now for sequence currents in the transmission line L2, BA0 at bus 2 is equal to 0.435 per unit, BA1 at bus 2 0.5641 per unit, BA2 is at bus 2 is 0.2046 per unit, BA0 at bus 4 is equal to BA1 at bus 4, BA2 at bus 4 equal to 0.3195 per unit. So from this sequence voltages at buses 2 and 4, we can compute for the sequence currents at the transmission line L2. IA0 is equal to 0.0435 minus 0.3195 divided by J 0.6. And that gives us J 0.46 per unit for IA0. IA1 is equal to 0.5641 minus 0.3195 divided by J 0.30. And that gives us negative J 0.8156 per unit for IA1. IA2 is equal to 0.2046 minus 0.3195 over J 0.30 equal to J 0.3828 per unit. So from there, we can now compute for the phase currents in transmission line L2. IA, IB, and IC can now be computed using the product of the A matrix and the sequence currents. IA is equal to J 0.0273 per unit, IB is equal to negative 1.0378 plus J 0.6764 per unit, and IC is equal to 1.0378 plus J 0.6764 per unit. Now for transmission line L3, the sequence currents in transmission line L3 that will be equal to, if the sequence voltages at buses 2 and 3 are already known, and at bus 4 we already had computed for this sequence voltages at bus 3 and bus 4. IA0 now, IA1 and IA2 can now be computed. IA0 is equal to 0.1101 minus 0.3195 over J 0.40, and that gives us J 0.5235 per unit. IA1 is equal to 0.5271 minus 0.3195 all over J 0.20, and that gives us negative J 1.0383 per unit. And IA2, that is 0.2220 minus 0.3195 all over J 0.20, and that gives us J 0.4874 per unit. So thus, we can now convert to phase currents in the transmission line. We can now be able to compute for the phase currents in transmission line L3. IA, IB, and IC can now be computed using the product of the A matrix and the sequence currents. IA will give us a magnitude of negative J 0.0273 per unit, IB equal to negative 1.3213 plus J 0.7990 per unit, and IC equal to negative or positive rather 1.3213 plus J 0.799 per unit. That ends our module 16, and see you in our next module.